data structures for disjoint sets. First, I will introduce disjoint sets and disjoint set operations and an application of disjoint set data structures. And finally, I will show you how to implement efficiently those disjoint set data structures. Disjoint sets. Two sets, A and B, are disjoint if their intersection is empty. For example, A has two elements, 1 and 2, and B has two elements, 3 and 4. Then their intersection is an empty set. So they are disjoint. Multiple sets sets from A sub 1 to A sub k are disjoint if every two distinct sets are disjoint. For example, S1 has 1, 2, and 3, S2 has 4 and 8, and S3 has 5 and 7. Then S1 and S2 are disjoint, and S2 and S3 are disjoint, and S1 and S3 are disjoint. So these three sets are disjoint. We define a collection of disjoint sets. A collection of disjoint sets is a set of disjoint sets. For example, this set is a collection of disjoint sets. We use the term collection not to be confused with the term set. Basically, this is a set of sets, but to distinguish them, we use this term collection. And each set in a collection has a representative member, and the set is identified by the member. For example, 1 is the representative member of this set, and 4 is the representative member of this set, and 7 is the representative member of the last set. Each set has only one representative member. Okay, and a collection of dynamic disjoint sets. Dynamic means sets are changing. For example, new sets can be created. Originally, we have 3 sets, but a new set is created. Or 2 sets can be united. In this case, these 2 sets are united into one set. So these 3 operations are major disjoint set operations: make set, union, and find set. These input parameters are set elements. Let me explain them one by one. Make set of X is like this. Given a member X, generate a set for the given member X. For example, make set of 9 is this. We create a new set including only member 9. This is the make set operation. And union operation is unite two sets. Union 1 and 4 is like this. Okay, there are two sets. This set includes 1 and this set includes 4. If we do this union operation, these two sets are united into one set. And we select a new representative member, because before the union we had two representative members, but after the union only one representative member should be assigned. In this case, we used 1 and 4, and they are representative members. But union 2 and 4 or 2 and 8 is possible. We don't have to use the representative members. We can use any members. And finally, find the set of x. Find the set of x is like this. Find the representative of the set containing x. So this operation, find the set of 5, is first find the set including 5, and then return the representative member of the set. So we return 7. Okay, I explained several terms, and they are basically simple. And now I'll define a problem. This problem is developing data structures to maintain a collection of dynamic disjoint sets supporting disjoint set operations, which are make set, union, and find set. Okay, first I'll introduce some parameters for running time analysis. The number of make set operations is denoted by n, and the number of union operations is denoted by u, and the number of find set operations are denoted by f. And the sum of these operations are denoted by m, which is the number of total operations. Okay. Look at this. U is at most n minus 1. What does it mean? 박종훈, 박근배. Okay, can you explain the meaning of this inequality? U is at most n minus 1. What is U? 김범진, 장영민. Yes, the number of union operations. What is n?
n 같은 경우는 지금 가지고 있는 세트의 숫자인데, 만약 세트가 각각 하나의 멤버만 가지고 있다 그러면은 그 멤버 전체를 합치는, 그러니까 멤버 전체.
Okay, but n is not the number of sets. N is the number of
n이 그 뭐야
n is the number of make-set operations. Okay? And when we call the function, the operation make-set, it has only one member. So the number of make-set operations is the same as the number of all members in the collection. Okay? So in this case, n is 7. So to create 7 members, we need 7 make-set operations. Okay? Okay, then there is an important property that the number of union operations is at most the number of members minus 1. Why? Each union operation reduces the number of sets by 1. So after n minus 1 union operations, we have only one set. And then we cannot do any union operation more. So n minus 1 is the maximum number of union operations. Okay, so to analysis the running time of this disjoint-set operation, this fact is very important. And from now on, we assume that the first n operations make-set operations. That is, every member is created for the first time. And then we union. And then I will explain an application of disjoint-set data structures. A well-known application is computing connected component. First, let's consider a static graph. That is, the graph doesn't change. The number of vertices and edges are given in advance. Then we can find all connected components in theta of v plus e time using the depth first search. Okay, think it over and how we can find all connected components using the DFS. As far as I know, this was your programming assignment, right? And the deadline of programming assignments is today. But some student told me that they have a lot of exams this week. 3 exams. I don't know why. So I will extend the deadline of the programming assignment. I'm not sure. In the middle of next week or at the end of next week. First, we start the DFS by selecting an arbitrary vertex. Assume that this one is selected first. Then, connected components are defined on undirected graphs. So this is an undirected graph. So we start the DFS from here. Then, before this vertex becomes black, we visit all vertices in this connected component. All right? So we can visit all vertices in the same connected component. Then we mark these vertices are from connected component 1. So a connected component is discovered. And then we select another white vertex. Okay, it is maybe this or this. Then assume that this one is selected. Then we start the DFS from here. Then we can visit these two vertices. Then these two vertices are in connected component 2. In this way, we can find all connected components using the DFS. It's very simple, right? Then let's think about a dynamic graph. Dynamic graph is like this. A new vertex, possibly a new edge, can be added. Or an edge some edges and vertices can be eliminated. In this case, if we use the DFS, then we have to search all the vertices and edges again. And it takes another round of DFS. But look at this simple case. This edge is added. And if we maintain the information that there are two connected components, we can easily determine the connected component of this new graph. There is only one connected component in this graph. So that's the main idea. If we maintain a disjoint set data structure, then finding connected components is very efficient. Look at this. How many connected components are in this graph? 손광훈. Okay, what is the number of connected components? Yes, there are 4 connected components. They are A, B, C, D, E, F, G, H, I, and J. And they are represented by a collection of disjoint sets. Okay? And then suddenly a new edge is introduced into this graph. Then these two connected components are united. So after the introduction of this edge, there are only 3 disjoint sets by uniting these 2 sets. So only one union operation is enough. But if we use the DFS from scratch, then the running time becomes theta of V plus E. So this is why we have to develop a data structure for disjoint sets. Okay, if we use the union operation, just union H and J is enough to find the new connected components. Okay, this is the pseudocode for computing connected components using disjoint set operations. Okay. Okay, try to understand this pseudocode. Yes, we create a number of sets, and each set has only one vertex. So for each vertex, we create a set, including only that vertex. And then these three lines. No? 김현준.
그 엣지 그래프의 엣지들을 다 봐서 그게 연결돼 있으면은 그냥 연결돼 있으면은
For each edge, what is the meaning of this? If find set of U isn't
U랑 V의 그 U가 속해 있는 집합의 representative랑 V가 속해 있는 거가 다르면은
Yes.
그 두 개를 묶어줘요.
Yes. So U and V were in different connected components. We unite those two connected components. If they were in the same connected component, we don't have to do anything. Okay, then let me show you an example using the pseudocode. Initially, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 sets. And each set has each vertex. So first, we use this edge between B and D. Then, because B and D are in different sets, the two sets are united. And then this set E and G, this edge between E and G. And then these two sets are united. Next, AC, we do the same thing, AC. Next, H and I are united. AB, look at this. A is included in this set and B is included in this set. So they are in different sets, so they are united. And the result is a new set, A, B, C, D. Next, E, F. Yes, we do the same thing. How about this? B, C. In this case, B and C are already in the same set, so we don't do anything. They remain the same. Okay, done. So this is how the disjoint set operations are used to find connected components. And this is a simple pseudocode to check if two vertices U and V are in the same connected components. What's that? Can you explain this pseudocode? Okay, they check if the two vertices are in the same set or not, but what is the main idea to check? The representative member of U and the representative member of V. So if they are in the same set, their representative members are the same. Okay, right. Okay, so now it's time to explain how to implement an efficient disjoint set data structure. I'll explain two data structures. First one is a linked list representation. Second one is a forest representation. So this is the best. This one is better than this, but this one is sometimes useful. So I'll explain two representations. In the linked list representation, each set is represented by a linked list, and members of a disjoint set are objects in the list. And the first object in the linked list is the representative, and all objects have pointers to the representative. Okay, let me explain using this example. So this is a collection of two disjoint sets. One has B, C, E, and H, and the other has D, F, and G. So because there are two sets, we need two linked lists. This is the linked list for the first set, and this is the linked list for the second set. Because it has 4 members, this linked list has 4 nodes. C, H, E, B. And this is a pointer to the next node, and it has an additional pointer to its representative. And we have 2 pointers. One points to the head of the list, which is the representative member, and the other is the tail list, tail of this linked list. Okay. Then I'll explain 3 disjoint set operations. First one is the make set of X. Make set of X takes constant time. Why? We create a node having only X, and it has no next node, so it becomes the head. It becomes both the head and tail of the list, and it also becomes the representative member of the list. Okay, this is the make set operation. How about find set? In this case, it's simple, so let's get back to the general case. Find set of E takes constant time. Why? We just follow this pointer and return C as the result. So, thanks to these pointers, we can find the representative member in constant time. Okay? And union. Union is like this. We have 2 linked lists. After the union, the result is like this. So think about the time complexity of the union operation. Yes, more exactly. So you missed one important thing. In this case, we remove this head and this tail, right? So this becomes the head, and this becomes the tail, right? We remove this head and this tail, and then we have to connect E and F. So this is null, but after the union, this points to this node. Then the two, they are connected. And then there should be only one representative member. So F and D should point to B as their representative members. Okay, then we get this linked list. 한상현, what is the time complexity of this union operation? Yes, the number of the number of nodes in the attached linked list. Okay? So the running time is theta of m sub 2, where m sub 2 is the number of objects in the linked list being attached. Then let's analyze the running time for m operations. We have assumed that we have n members and F find set operations and U union operations. First, a simple and naive implementation of union takes n plus FW squared time. Okay, try to understand this. Okay, each makes an operation takes constant time, and there are n makes an operation, so it's n. Okay, then yes, there are F find set operations, and find set operation also takes constant time. So make sets and find sets are all can be done in n plus f time. Okay, then next, union operations. Why the running time is u squared? Assume that there are 5 vertices. The first, we merge these 2 vertices, and then we attach this list to a list with only one node. Then we have to change the representative pointers. Then we can create a list with 3 vertices, 3 nodes. And then this becomes the next representative, and we attach this to this single list. And then what is the running time? So first, it takes 1, then 2, then 3. So the whole running time is up to n minus 1, so which is n squared. That's why, so it is n plus f plus n u squared, and as I told you, u is at most n minus 1. So it is n squared. And then this is n squared, and we know that n plus f is at most m. So the running time is reduced to peak O of m plus n squared. And then we can reduce the running time of this into m plus n log n by using a weighted union heuristic. It means we can improve the union operation by a smart idea. It's simple. What would it be? You can guess. When we perform the union operations, we attach short list to long list. Then we can reduce the number of pointer changes during the union. Okay? It's very intuitive. Okay? So let's get back to the example. Okay, this list has 3 members and this list has 2 members. So we attach this short list to long list. Then we can reduce the pointer updates. Okay, this idea is very simple. Okay, then can you explain that the running time is reduced to n log n from n squared? It isn't easy to understand. I think this is the hardest part of this today. It won't be easy. We attach short list to long list, and it reduces the running time from n squared to n log n. Is there anyone who can explain this? Any volunteer?
이 경우에서는 이제 이 셋의 크기를 보고 작은 쪽의 셋을 큰 쪽으로 흡수시킨다는 개념인데, 그러면 가장 최악의 경우는 비교하는 셋이 계속 사이즈가 같을 경우입니다. 그렇기 때문에 그럼 어떤 상황이 되냐면, 예를 들면 이제 크로노트식으로 계속 셋이 반으로 줄어든 상태인데요. 8개의 상태를 보면 이런 식으로 합쳐지고, 충분으로 하나의 셋이 만들어졌는데, 이제 그렇게 되면 저희가 이제 트리에 바이너리 트리에서 때 배운 것처럼 이 뎁스의 길이는 로그 n이고, 그리고 이제 한 뎁스마다 전체 원소의 절반이 딴 쪽에 흡수가 되기 때문에 유니온에서는 2분의 1입니다. 그래서 이거 두 개 곱하면 2분의 1 n 로그 n에서 보신 것처럼 이제 이고 u n 로그 1가 됩니다.
Okay, good. The main idea is this. Let's give him a big hand. Yes, but I will explain some detail. So what is missing is we have to show that this is the worst case. So it cannot, sometimes it is not so easy. Okay, so main idea is like this. And think about, okay, this picture is good. Okay, this is a node, this is a node. Then let's count the number of pointer changes of this node. And there are at most log n changes for each vertex. Why? Because every time the pointer of a vertex is changed, the united set is at least double or more. So log n pointer changes means it is included a whole set. Then if we explain it in this way, we don't have to show that this is the worst case. Can you see the difference? Okay, the analysis is not level by level analysis. It's a vertical analysis. So let's think about this the whole process as a whole, and then originally it is in a set, in a single set, and then finally it is included in a big set, and it has n elements. Okay? Then let's count the number of representative pointer changes of this node. Then it is at most log n. Why? It means it experienced log n log u union operations, and every union operation makes the set double or more. Okay? So after this class, you can ask me about it. So it isn't easy to understand. But as a big picture, this is right. This is the worst case, and it's n log n. And I'll explain the forest representation. It is the famous representation. In this representation, each set is represented by a tree. And each member points to its parent, and the root of the tree is the representative. Look at this. There are two sets, so we have two trees. And B, C, E, H are stored in this tree. Look at the direction. So the children points to their parents, and the root points to itself. And this. Then let's think about the make set and find set operations. Make set operation is simple. Oh, where is the? Sorry. Okay, one is missing. I'll draw. Make set operations is like this. We create a node including x and make this pointer. Then this is the result of make set operation. it takes constant time. And how about the find set operation? I told that the root of the tree is the representative. And this is the pseudocode. How can you do this? 송광훈, is this your second question or third question? Second, yes. Can you explain find set of X?
파인셋은 자기 대표값이 나올 때까지 자기 자신이 대표값일 때까지 자신의 부모를 계속
Yes. We check if its parent is itself. If it is, we return X as a parent. Otherwise, we recursively call find set X with its parents. And the union operation. So look at this. We have two trees, and when we unite, the result of the union operation is this. 권다운. Okay, can you explain the union operation? I don't think it is difficult. So, yes, there are two representatives, but one representative points to other representative. Then done. That's all. That's union. But we can use the same idea when we perform union. The main idea is attach the shorter tree to the higher tree. So the similar idea. But actually, this is approximately true, but not exactly. Sometimes we attach higher tree to shorter trees. So more exactly, each node maintains a rank, which is an upper bound on the height of the node. And compare the ranks of two roots and attach the tree whose root rank is smaller to the other. So we compare lengths of the roots, but this is an upper bound of a height, not the exact tree height. So this is union operation. Union X and Y is link, find a set of X and find a set of Y. So these are two roots in the forest of X and Y. And link X and Y is this. We first compare their ranks and then we attach using this link operation. So let's compare this forest representation with the linked list representation. In this case, union is constant. Union takes constant time, right? But find set takes its height, right? But in the linked list operation, find set takes constant time and union takes longer, okay? So this representation makes the find set slow. So there is a technique to enhance the find set operation. It is path compression. It is this. Okay, assume that this is the original for tree. And then the operation is find the set of A. Then after the find set operation, we change the parent A to F. Then the next find set of A takes constant time. Moreover, we change all parents in the path from A to F. Then all find set operations on these nodes take constant time. It's path compression. So using these two techniques combined, union by rank and path compression, its running time is big O of m alpha of n. This is a very slowly increasing function. So in all practical situations, alpha of n doesn't exceed 4. So this value can be considered as a constant. So this is almost almost linear, big O of m. But the analysis of this forest representation is very, very difficult. So I don't consider the analysis this time. Okay, so I explained linked list representation and forest representation. Forest representation is useful. So use forest representation almost every case. But the analysis is very difficult, so I skipped the analysis. Okay, the final exam day is December 13th at 8:30 p.m. It is announced on our website. Is it announced? So it will be announced. So if you have an overlap with other exam, you can come late, at least 9 p.m. I'll give you an additional time. Okay. Then let's call it a day and see you next week.